17 people online? Okay, nice, cool.
So if people online have questions, I think also feel free to interrupt, right?
Oh, yeah, perfect, yeah.
Yeah, if people online have questions, just interrupt, and yeah. So thank you, and
thanks, Roger. Yeah, it's a pleasure for me to be here, and right, so it's January the 6th, so trying to warm up, of course, after holiday, New Year's, and Christmas. So yeah, in this first lecture, I'm just gonna briefly go through some slides, and I also have some notes. So the slides are exactly the same that I have shown in like a couple of weeks ago in this in the workshop we had here in Brazil. So just to catch up and to warm up. But then, if you don't understand anything in the slides, like I'm gonna go slowly through the points. I prepare some notes. So yeah. So okay. So the first point, let's go through the whole idea that's, okay, so we know we have amazing data coming from CMB and structure formation. So on the left, you see the amazing CMB experience that we have, and on the right, you see the LSS experience that we have. So something we hear a lot is that we live in the age of precise data, that we have a lot of data, and we should be able to catch up and to provide something that can actually catch up and constrain cosmology and be able to provide results. So instead of focusing on precise data, which is not the topic of my research, I'm going to talk about precise theory, which is the other side of the coin. So how to provide precise theory to be able to catch up and to basically constrain cosmology. So we know that structure formation, when we think about structure formation, we think about correlators in the sky. So we have galaxies in the sky, and we can take points 2 by 2 here in this case, just flashing here the results, and we can construct something called the correlation function, in which we see here a peak, which is the BAO peak. So instead of thinking about 2-point functions, we can generically think about n-point functions, in which we take correlators of n galaxy density field. So delta G here is the galaxy density field. And then we look in the sky. So here you see the redshift space sky, and we can think about correlators in this sky. So taking density fields here in this sky and constructing not only 2 by 2 points here, but thinking about n by n points. So you can go to 3 by 3 points, which is the bispectrum, 4 by 4 points, which is the trispectrum, and think about generically about n-point correlators, which basically embrace the whole information about delta G, the galaxy density field, which is the ultimate object we are interested in. So as I said, when we think about n-point functions, there are 2 ways to think about how to analyze this kind of plot. So here I'm showing the power spectrum, and what you see are 2 different perspectives on the same problem. So when we think about precise data, we actually go from the smallest scales for which we have a lot of data, and thinking about how to reach larger scales. So this is the experimentalist perspective, how to push towards the larger scales, large volumes, such that we are able to reduce the error bars here on this part of this plot. So here in this region, we have a lot of data, but providing good theory is actually quite hard because we are in the nonlinear regime, which means we should actually think about how, as a theorist, we should think about the other way, which is going from the larger scales in which the things are linear towards the small scales. So K here is the scale. So K is the inverse of distance, so it's 1 over a megaparsec. So you can read this as the K wavelength mode. So as a theorist, we go normally from this direction in which we don't have actually good data towards smaller scales. So how to take this bar and push to the right. So as I said, we focus generically on n-point functions, so the 2-point function, the 3-point function, and we can construct something not only like the 2-point function that I'm showing here, but also the bispectrum, which is a function of 3 wave numbers, K1, 2, and 3. And it's, of course, more complicated, but we should think about a generic way to predict things, not only for the 2-point function. So you can, of course, come, like, as you see, the 2-point function is quite simple, right? But when you go generically to n-point functions, which is a function of 5 different numbers, which are the K and the angles between those Ks, it becomes more complicated because then you have to have a consistent model that can embrace the whole information on the generic 3-point function. So fitting something here is actually quite simple, but thinking about something generic that you can extrapolate not only to the 2-point function, but towards higher n-point functions is actually more complicated. So the question I'm going to address here in this lecture is there any systematic way from first principles that you can push this bar towards the small scales, towards the nonlinear scales? So this is the generic Eulerian equations that we have for perturbation theory, and here I have the equations describing the density field, delta, and the velocity divergence field, which is theta. So here what you see is an equation for delta, which is delta t of delta, equals to something which is a source here on the right-hand side, which is a nonlinear source because you have a coupling between delta and theta. And here, similarly, for the velocity equation, we have something like delta t of theta equals to something like theta coupled via a beta coupling. So what you see here is an alpha coupling between P1 and P2, and a beta coupling between P1 and P2 again. So this is the nonlinear part of the equations, which makes things more complicated. Of course, you can just cut this, linearize the equations, and solve for the linear theory. But if you want to push towards the smaller scales, towards the region in which we can gain information about BO, for instance, you should think about including these couplings here, and then things become more complicated. So to solve this equation, we can actually come with some perturbative ansatz in which A here is the scale factor to a power of n, so time decouples from space in ice and the sphere. I'm going to explore this in the notes later. But delta n here is just a function, a convolution with a kernel f with n entries of delta 1, which is the linear solution for here. So delta 1, whenever I write delta 1, it's just the linearized equation here, the solution for the linearized equation in which you don't have the right-hand side. So there's a lot of people that have worked on this. I just refer here to some names. So the idea here is then to plug these ansatz in this equation and solve order by order those equations. So this is the general spirit of how EFT of LSS works. So first, what happens if we just naively plug these ansatz onto the equation? So what I'm showing you here is the loop calculation. So as you see, we're going to get some loops. I'm going to explain what those loops are, what exactly are the meaning of those loops. And what you see here is that when you take cross correlations of delta n and delta n, you reach those loops. But something we find that's quite funny is that when you look at the size of those loops, like what I'm showing here is P0, which is the linear theory, as you see in black. And then you see P1, P2, P3, which are the loop calculations that you gain. And we find something quite funny, which is the third order loop, like the tree loop contribution, is actually larger than the second loop order and the first loop order. So we see something really interesting, which is the fact that the series doesn't behave very well. The fact that if you add a contribution, so imagine you have a Taylor in which the third term contributes more than the first term. So this is something similar to what we see here. So there's something actually wrong here that we have to fix. So how to fix this is actually what we call effective field theory, and you have to add some terms to those loops to actually account for how small scale behaves and how small scale interacts and affect those loop calculations. So a second problem which I'm showing in this plot. Yeah.
When you say perturbation, usually in quantum field theory or any other theory, you have a parameter that you're expanding on that's small. Selective charge or alpha, which is 1/137.
Right.
In this case, not clear because you're making an expansion on deltas, say, order by order.
Yeah.
But it's not clear what is the parameter, the perturbative parameter.
So delta 1, we are quite sure delta 1 is small on large scales. So this is something we are quite sure. We are quite sure that when you take those loops here, you're going to get contractions of delta 1 with delta 1, which means you have an expansion, a systematic expansion in the number count of delta 1s here. So this is the...
The parameter then depends on the scale.
Right, right.
So also in QED, alpha depends on the scale.
Yeah.
In QCD, alpha S also depends on the scale. So in that sense, the analogy goes through. Yeah.
Right, so for each one of those cases, you have an expansion, like the expansion parameter changes, that's true. So this is delta 1, and the variance of the field, which is delta 1 cross-correlated with delta 1, changes as a function of scale. But you're quite sure that as you move towards... So this is the same as we do in perturbation theory for fields, right? We're expanding over fields here. That's different than in the case of quantum field theory, in which we have an expansion over, lambda or something like this, right? But here we're quite sure that delta 1 has to be small on large scales. So we know this perturbation has to break down as you move towards smaller scales, but we're quite sure also that it has to work because delta 1 is small on when k goes to 0. So delta 1 is the expansion parameter here. Yeah, and also not only delta 1 is an expansion parameter, but we're going to see that derivatives of delta 1, which come with an extra k, so delta x of delta 1, which is basically in Fourier space k times delta 1, k as you move towards k going to 0, this is also small. So there is a double expansion here, both in k and in delta 1. Okay? So I'm just flashing here the loops. So one loop, you have these two types of diagrams. I'm going to explain how you get those diagrams.
So the boxes are basically off the matrix, right?
The boxes here? Yeah.
Can you think of alpha and beta as expansion parameters?
Not really, because the coupling is not something that, so I'm going to show that alpha and beta can be whatever you want. So it's not necessarily, like, you're not expanding over the vertex here, you're expanding over the fields.
Right, but if you go to higher loops, you can have more vertices, so if alpha is very large, then it's not going to work.
So you're thinking about divergence inside the loops here. And we can actually show there is actually the IR divergence that appear here are not relevant because they cancel out when you sum over all the loops. And also the UV divergence that appear can be, I mean, in the case of lambda CDM, there is no divergence. But even if they were there, you can cancel them out by counter terms. So I'm going to explain what the counter terms are next. But so yeah, they don't diverge. Long story short, they don't diverge. So what you have here is the one loop contributions. What we have here are the two loop contributions, which are 4 diagrams. For the 3 loop, it gets more complicated, more nasty. But so, of course, computing those things is also pretty hard. It's a project per se. So computing these integrals here, so those are 2-dimensional integrals. Those are 5-dimensional integrals. And going to P3 loops, those are 8-dimensional integrals. So this demands a lot of time. And you have to compute numerically. I'm going to talk about this next. There are some alternatives to bootstrap this and compute the things analytically. But for the 3 loop and 2 loop so far, we can only compute them numerically, and those are quite expensive. Sorry, Danny. Yeah.
But then the thing on the bottom, somehow it's another assumption that it's somehow saying that you're computing everything with respect to the knowledge of the linear field.
Yeah.
You need to compute some f functions that are coming from this kind of thing.
Yeah, perfect.
But then it's like another kind of answer.
Well, here it's not an ansatz. You just, so if you want to solve order by order, you actually have to have products of delta 1s, right? So this is what appears. So you first linearize the equation, and of course, like, you solve this as an ansatz, but you can see that this is what has to appear, like products of delta 1. So linearizing means dropping the right-hand side here and solving just for this part of the equation. I'm gonna do it in the blackboard. So if you don't get it, like, I'm gonna do it slower. Yeah, it's coming. Right, so this f, I'm going to also show how this f looks like and how to get the solution for this f. But just to know that this is just a product of the wave vectors that you have here, q1 and qn. So this is a dimensionless guy, so it has to involve ratios of q1 and qn, okay? Right, so what you see here, yeah, as I was saying, computing those guys is also very expensive numerically. So to compute the 3 loop, for instance, for each one of the K modes, you have to wait more than 1 day. So it's very expensive. So it's something really hard to put inside something like an MCMC. So it's something that we have to think about how to push. If we want to push to higher loops, we have to think about smarter ways. And this is something, yeah, I'm going to explain. I've been thinking about it too. So what you see here on the right is a second problem of this perturbative series, which is the fact that whenever you do this expansion, so this expansion in terms of delta 1, you actually have a lambda dependence here. So whenever you compute those loops numerically, there is actually a hard cutoff here. So there is a lambda you have to put here. And I didn't put the lambdas now. They're appearing in the next slides. But when you compute this, it actually depends on the cutoff you put here for computing those. So you have to basically truncate those delta 1s here on some scale, which means each one of those p's will depend on the scale you truncate. So you can just think, okay, I don't care about it. I can just take lambda and bring to infinity and take the harder, like the high cutoff limit here, P3. But as you see, the fact that it depends on the cutoff you choose and if it actually converges or not depends on the cosmology. So how can it be that the P that you calculate that's something physical depend on some arbitrary choice that you have, which is the cutoff you put here to calculate something. So this lambda that you put here cannot be physical, so it has to be something that has to be canceled out. And yeah. For P1 and P2, yeah, it depends. It depends more than with the cutoff, definitely, because here you have 3 entries. But yeah, that's true. Yeah. Each one of the deltas here has a common lambda. So here, there are different ways to put lambdas here. You can either put lambdas as a single lambda here in the integral, so basically a hard cut in the momenta, or you can put lambdas over each one of the fields. So whether you put the lambda here or if you put lambdas directly on the fields is something that relates to the renormalization scheme that you choose in the context of quantum field theory. And so you want each one of the terms here to be independent of lambda 2. In the end, it's the same. I'm going to show it's the same, but yeah. Because the counter terms that cancel out one of the delta n's here is going to cancel some other delta n's as well. So in the end, you think about it at the level of the correlators and not at the level of delta n's. Yeah, definitely. So same way as in QFT, you have this MS scheme, MS bar, and all the other different schemes here. As I said, you can either put a lambda here, or you can put a lambda in each one of the fields. Or dim-reg. You can think about dim-reg as well. So yeah, there are different ways to regularize the theory. Right, so back to the slide. So this was the slide I had before, but now we have to think about something else, which is adding a lambda to those fields. So here I'm adding a lambda to each one of the equations, which is basically accounts for smoothing the equations on a scale lambda, and accounting for something we don't know, which is, so this equation, as I'm going to explain, has some limitations, which is the fact that we have assumed to derive those equations a perfect fluid approximation. So it basically has something missing here on the right-hand side, which is the small scale contributions. So actually on those scales, in those equations, there is something missing, which is how small scale fields couple to each other, and how we have a physical descriptions of those couplings. So this description that's missing here, so this small scale contribution that is missing here, can be translated in terms of this expansion here by adding some counter terms that depend on lambda. I'm going to explain how those counter terms look like, but the idea is that basically you add something here that cancels out the lambda dependence that you generically have onto those loops. So as I said, you have a lambda here in this delta n, but also you have to cancel this lambda dependence such that this guy on the left-hand side doesn't depend on lambda. Okay? So the idea is that everything here cannot depend, everything on this side cannot depend on arbitrary choices you make on the right-hand side. Yeah. Yeah, all those gauge dependence will appear more when you go to larger scales. So when you think about relativistic effects, such as those that Carol here works on. So when you think about gauge, so here we are pretty deep inside the horizon, so we don't suffer from those gauge dependence. Yeah. So it means that dark matter, we know dark matter is collisionless, right? So the fact that dark matter is collisionless means that whenever you take different fluid lines, so when you think about the fluid like, so perfect fluid means you don't have any velocity dispersion, right? At every single point in the sky, you have basically a stream of lines that go parallel to each other. So you can associate each point basically in the fluid component as having one single velocity, right? So you have no velocity dispersion. When you think about collisionless dark matter, we have something like dark matter lines can cross each other. So this is something like shell crossing, which means that for one single point in the sky, you can have basically a velocity dispersion here at this point. Okay.
Also anisotropic stress, right? They're going to,
Yeah.
it's going to influence the anisotropic stress.
Yeah, definitely. So this generates an isotropic stress. Right. So the fact that we don't know which lambda to put here is actually something that's quite independent on the K modes that we choose. So K, which are these long wavelength fluctuations that we have. So we can see here in this picture that basically Van Gogh already knew about EFTs, right? So the fluid picture that we see a fluid stream here in this direction, right? And we don't care about the size of the brush that you use. So lambda here would be the size of the brush, which is basically the thickness of this brush that you use. But when you think about long wavelength fluctuations, so there's a clear separation of scale between K, which are those long wavelength fluctuations, and lambda, which are small scale fluctuations. So nothing that happens here on very small scale can affect something that happens on large scales. And if it happens, it has to happen via something that we know how, but via the symmetries of the problem. So we know how these things affect these K modes via the symmetries of gravity. So we can actually think about how we can still see the lines and we can still see the fluid lines on large scales despite not knowing exactly the dynamics on scales lambda. So the idea that we have here is a clear separation of scales. Right, so when we add something that depends on lambda, and when you add those counter terms, we actually restore how the series should behave. So you see here the same P's that we had before, so P1 loop, P2 loop, and P3 loop, after adding those counter terms. So what happens to the series when we add those counter terms is that basically it restores how things should behave. So you see here that P1, which is the one loop correction to the linear spectrum, is actually now larger in absolute value, of course, than the second loop contribution, which is larger than the three loop contribution, at least on large scale. So here we're just adding the first counter terms. And you see that on large scales, after adding those counter terms, everything is fixed. And everything behaves as it should behave. Okay? A second problem which I'm going to address, okay, I was so far thinking about matter. So this, when I think about this P, this is the correlator of matter-matter. So this is density-density correlator. So a second problem that we have is that when we look at the sky, we actually don't observe matter directly. We observe something like which are tracers of matter. So we observe something like galaxies, baryons, and things like this. So we have to relate how baryons behave to how dark matter behaves. So how to connect those two different fields, which are the baryonic field and the dark matter field, for instance. So the way to connect those things come with the name of the galaxy bias expansion. So the bias expansion is a way to write down delta G, which is the galaxy density field, as a function of the dark matter density field. So this is the ratio between the number density of galaxies over the background number density minus 1. And the way we write down this expansion is an expansion in terms of operators O. So this is what's called in the context of high energy physics as an OPE, an operator product expansion. So we have generic operators O. I'm going to explain what those O's are. And we have some stochastic field epsilon, which I'm going to develop later too. But the idea is that you have an expansion in terms of bias parameters and stochastic parameters here, in which we encapsulate the whole information that connects. Basically, this O can only depend on the matter density field. So we can connect here O with delta G. This O is going to be products of the gravitational potential. And what we can connect here is then the delta G, which is the galaxy that we observe, to something that's the matter and the potential, the gravitational potential that you have. So I'm going to explain the bias expansion also. But the general idea is that this relation is what we call this OPE, which is an operator product expansion, in which we use basically the GR symmetries to explain, to understand how this operator expansion works. So at first order, we have something which is delta, the density of matter. At second order, we have the density of matter square, and also G2, which is a Galilean operator. I'm going to explain what it is later. And at third order, we have something which is delta cubic, and also products of delta and G2, and some other guys I'm going to explain later. But generically, we can write down these O's as a function of delta, which is the matter density field, as some convolution of some SO kernels times delta that appears n times for an operator that's order n. So we can also think about some perturbative expansion for each one of those operators, which allows us to write down and to relate basically galaxies that we observe to the matter underlying density field. So finally, to finish this part, so this is just going to be an introduction, then I'm going to move to the blackboard. So the reason we have to think about what's the reason why to do this perturbative approach and not to do something like simulations and other things. And the reason number 0 for me is because we have fun calculating all those loops and those complicated guys. So this is something that can be actually quite interesting and quite, you can think about, divergence, you can think about how to cancel out those lambda, and there's a lot of things to be done and a lot of things to think about and to understand about physics when we calculate those loops. But when we think about what we can gain in cosmology by doing this, there's actually many reasons why to do it. First, when we think about doing this loop expansion and this perturbative expansion, it means basically almost exhausting the whole information we get, at least when we think about galaxy clustering. So when we think about galaxy clustering, the whole information is basically limited by shot noise. And at least in the scales in which we are not limited by shot noise, using perturbation theory basically accounts for basically exhausting the whole information that we have in the galaxy density field. Of course, when you think about lensing and other things, we can think about non-perturbative ways, such as simulations. But at least for galaxy clustering, before reaching shot noise scales, doing perturbative expansion is basically all you can get in terms of information. Second, it's very robust, which means we're quite sure we are not missing anything, because the only assumptions we have here are the symmetries of GR and the dynamics of dark matter fluid. So we're quite sure we are not missing anything, different than running a simulation in which you're never 100% sure you're not missing some parts of the problem. Of course, like there are some things you can check. In simulations also, there is ways to be sure, but at least it's a very conservative way to include all the operators that have to be in the problem and to understand how physically they behave. And what I mean by physically, it means also to construct something which is analytical, which means you can take derivatives with respect to those loop calculations, right? And having some analytical understanding about this is something we aim for, because it means we can actually, for instance, take derivatives and put that in a feature or put something like this, which means you have full control of what's going on. If you change some parameters, for instance, if you smoothly change something, you understand how it appears in the EFT story. Also, it's quite easy to extend to other models. So if you think about not only lambda CDM, but if you include other components, it's quite easy to generalize and to include other types of interactions in the vertex of EFT of LSS. So when you think about, I don't know, interaction between some extra dark radiation component and dark matter, it's something quite easy to understand. I also think about modifications in GR, it's going to introduce new vertices, but you also know how to include those new vertices. Of course, the story becomes more complicated as you go away from lambda CDM, but it's also quite easy to generalize, which means you don't have to construct, again, a whole new simulation package or a new simulation dynamics such that it embraces the whole physics. So you have 100% sure also on how to extend this, at least for some class of models. Right, so now I'm going to move to the blackboard and go through those points more carefully and explain, more slowly how to get to those loops. Okay? Yeah. Right. So for baryonic physics, as you said, the scale in which baryonic physics start to be important, it's actually something debatable. We can think about, okay, we don't know quite sure where this scale is, but we know that at least on large scales, it has to behave. So baryons and dark matter, we can think about them as two separate fluids. And we know that at least at leading order, it has to behave as something like the usual counter terms that we have. So the scale, the exact scale in which baryonic physics is relevant is something debatable, but the fact that it affects dark matter components, usually as a counterterm to, is not. So we know exactly that on large scales it has to behave exactly as the leading counterterm. So.
Sure, but then the scale at which effectively what is it in a sense limitations to the applicability of divided bench?
So you can always think about this double fluid component, and you can always think about, so two separate fluids, the baryonic fluid and the dark matter fluid. And you can always use this to modify the EFT story, also knowing how the baryonic physics affect the EFT. So there's a systematic way to think about how baryonic physics affect the dark matter component, at least. Which, of course, like the scale in which it breaks down, of course, changes as strong these baryonic effects are. But there is a systematic way to derive it. Okay?
Then it doubles the number of equations, right?
Yeah, yeah. You have a double fluid component, so you also have to account for these baryonic equations. Yeah.
It can be done analytically as well.
Yeah, at least at leading order, and yeah, it can be done. Okay, so then I'm gonna stop sharing my slides, I think, and move to the blackboard, right? Yeah. So you mean if you have these two components, if you change your right-hand side, which means adding new interactions for the baryonic physics? Yeah. 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 Yeah, so you would have, as Rogero said, instead of having just these equations here, you would have a second, like a doubled version of this equation. And at least for the baryonic part, on the right-hand side, you would have something like interactions. But for the matter component, which are those small scale contributions here, you know that the baryonic part can affect the dark matter part via those basically sigma ij, which also enters at leading order as something like a counterterm. Okay? Yeah. Yeah, exactly. Exactly. You can find an analytic solution for both system of equations coupled to each other. That's what you would have to do. Okay? Right, so then I'm going to stop sharing and move to the blackboard. So. Yeah, so first let me briefly go through the reference. So those are the notes I used to construct my own notes. So fortunately now there is a lot of reference you can follow. So the only book I think we have so far in this topic is this, The Modern Cosmology from Doddleson and Fabian Schmidt. So in chapter 12 now in the new version, so this is second edition, they have now a chapter focused on nonlinear structure formation. And also I followed those notes, so Tobias Baudov, Oliver Filkux, Misha Ivanov, Leonardo Senatore's notes, and also the bias review, also from Vincent de Jacques, Jong, and Fabian Schmidt. So you can follow, I don't know, different levels of complexity in those notes, so just open them and choose one, which are quite good. Huh? I think Fabian's book is very, yeah, he goes through everything very smoothly, so I can suggest this one. Right, so let me focus first on the conventions. So for the Fourier transformation, I'm going to use this convention here. Which is the normally used in the context of particle physics. So the one in which you don't have the pi's here when going from x, from k to x, but you have the pi's when you integrate, oh, sorry. So this is k. When going from x to k, but you have the pi's when you go, whenever you have a loop, whenever you have an integral here that goes with a k, you have a 2 pi cubic here downstairs. So and as a matter of notation, I'm gonna often omit this part and write everything as integral of k so convolutions, as you already saw, is something that is going to appear a lot of times. So for instance, if you have something like delta square of k, this is something like integral of p. Now I'm using this convention here in which I'm hiding the d3p over 2 pi cubic. And I'm going to use, let me, so this is just a convolution, okay? And often, so it's often easier, instead of dealing with p and k minus p, it's often easy to have two momentas, integrated p1 and p2. And write it down as this. So this is the Dirac delta function, and the hat here, I put a hat because the hat because just to hide the 2 pi factors again. So for the filtering part, I'm going to consider often a sharp k filter and f of lambda of k is just k. So this is a filter, f of k, in which w of k lambda is equal to a step function, a heaviside function, 1 minus k over lambda. With some 2 pi's here maybe missing, but that's it. For endpoint functions, we are going to use this convention in which delta k1, delta k2 is equal to delta hat of Dirac of k12. So there's a Dirac here because it accounts for basically displacement like invariant standard displacements. So there's a Dirac delta function here, delta k1, delta k2 prime. So we often use the prime notation to hide the 2 pi factors and the delta of Dirac here on this side, which is equal to k1. And generically, you can think about delta K1 delta Kn equals to something like n. Oh, sorry, I forgot to say that P1, 2 here is basically P1 plus P2. There's, of course, some arrows missing here. But I'm just using the n notation here to say that I'm summing over the momenta here. And depending on the case you have, this is the generic endpoint function. So this can be P or by the bispectrum or the trispectrum of K1, Kn. Right, so convention is over. So let me go through the matter part. More specifically, let me think about how going from Boltzmann to fluid. So the equation that we have, the Boltzmann equation, the Vlasov equation, is delta F, in which F is basically the distribution, the phase space distribution for matter. We can write down this as delta tau. We can write down the derivative as some partial derivatives plus P over MA del F del X minus AM del phi del F del P equals to 0. So as you see here, there is an assumption here which is collisionless. And it can take the moments of this distribution F, and we can define rho to be, of course, rho of X should be equal to M over A cubic integral d3p of F. So this is basically the zeroth moment of F. Vi, which is the first moment of F, is going to be integral d3p of pi ma f divided by integral. So just a normalization here of F. And so this is the first moment, and for the second moment, which is rho ij, which is equal to integral d3p pi pj divided by am f, again normalized by d3p of f minus vi vj. So those are the first moment, sorry, the zeroth moment, and the second moment, okay? Okay, I'm gonna erase this part now. So then you can take those moments and basically take integrals of the Vlasov equation with respect to P to get equations for, if you take one integral with respect to P, you get an equation for rho. If you get an integral of this multiplied by Pi, you get an equation for V. And you can also go through this to construct the whole Boltzmann hierarchy of equations. I'm not going to derive this, but in Dodelson's and Fabian book, they derive this and they get to of delta plus I'm going to put this 0 plus, so those are normally called continuity, and this is called Euler's equation. So here I'm using tau. So this is co-moving time. X is also co-moving. Yeah. Yeah, the A's are here. There is an age. I'm always using co-moving coordinates. So this age that you see here, so is also the co-moving Hubble. So this is A times age. Everything here is co-moving. Plus the third equation, which is the Poisson equation. So when we think about intuition, for those equations, it's actually rather simple. So for the first equation, which is continuity equation, we think about a generic box in which basically we have a density inside this box, delta, and the change in this density with time basically depends on the velocity on the boundaries of this box, right? So you have some velocities here. And basically, if you want to ask yourself how much the number density inside this box has changed, it's basically proportional to the velocity in the boundaries of this box, okay? And the intuition for the second equation, which Euler's equation, is basically the same, but instead of thinking about density here, we can think about the general momentum inside the box, and basically the change in this momentum is proportional to basically the second moment of the phase space distribution of our matter, so sigma ij. So basically the change in Vi here is basically proportional to sigma ij in the boundary of this box. And also gravity, of course, all the pressure terms that we have. So basically this term and this term, and all the other guys. So it's basically some conservative equations that tell you exactly how the density and the velocity change as you take basically a smooth part of the space. So far, there is only the collisionless assumption here. Yeah. So for the pressureless assumption, I'm going to have to drop this guy here. So this guy, when I drop this guy here, there's another assumption, which is that it's a pressureless perfect fluid. Okay. Yeah, I'm truncating the hierarchy here, and I'm saying, yes. So the truncation of the hierarchy of moments here, basically something called the BBJKI truncation, and it was shown that basically the only consistent way to truncate this is via keeping only those two equations. Otherwise, you cannot consistently truncate this because you source all the higher equivalents on this. But truncating this basically says that we don't have a time derivative equation. So of course, you could have a delta T of sigma ij, something like this. We're just neglecting this part here and truncate and saying basically we have a description for sigma ij that's, we are neglecting this part here in the pressureless perfect fluid approximation. Yeah. Yeah. You mean the some guy in the metric? So the only source of gravity we have here is this term. So there is an assumption here that GR is the only gravity, like we're assuming GR. So if you want to modify GR, you have to account for extra potentials here and add some extra part on this right-hand side of the equation. So this, of course, becomes more complicated. Is it clear? You can, of course, think about some extra, because if you want to modify GR, for instance, add in some extra degrees of freedom, you would have to add these degrees of freedom here, plus some equation that tells you how this degree of freedom change depending on the components. So you would have to have some extra component here, plus some extra equation that tells you how this extra potential change. Okay? Yeah. Yeah, the phase space distribution function. Yeah, definitely. Yeah. Yeah, if you assume some f distribution function for f, you can come up with a full equation here. But probably then it's going to become more complicated. If you want to go beyond the pressureless perfect fluid approximation, you would have to consider the full moments here and also solve for these extra moments. So for instance, for dark matter, we know that dark matter is collisionless, and this pressureless perfect fluid approximation breaks down at some scale. So this is the whole point of adding and modeling how this extra guy behaves. But the point is that when you go beyond the perfect fluid approximation, you also have to solve for something like here, for some extra hierarchy of equations here. And this becomes more complicated. But you can try to do it. There's actually some groups trying to UV complete. So this is calling UV complete in dark matter, right? So instead of considering it as a perfect fluid, you go beyond and consider it something like collisionless dark matter. And you assume, because then to go beyond this, you have to assume some velocity dispersion as well, right? And you can actually do that, and some people have tried to do it. So I can recommend a paper from a couple of years ago, which is Scottimaru. I think it's double R. Garni, Huber, in which they consider something called VPT, which is laws of perturbation theory, in which they go beyond this pressureless perfect fluid approximation and try to solve for the whole Boltzmann hierarchy of equations. So you can go beyond, and you try to UV complete. UV complete means assuming some phase space distribution there, and actually going back and trying to solve for the whole hierarchy. But then it becomes more complicated. So the consistent way to truncate this is to basically neglect and drop this second moments here and consider a set of, here you have two equations and two variables. The point is that if you add new equations here, they also become coupled to the next two leading order equations. So basically, if you consider this, you're also going to have to consider the next equation, which means you would have an infinity tower of equations, and you would have to solve for all of them together. So the only way to truncate, you can show, like this was shown, is to basically drop this term and to solve for the pressureless perfect fluid here. Okay? But you can try to go beyond. And actually what they did, I mean, they have two very lengthy but very complete papers in which they try to go beyond and explore UV scenarios in which you know and you assume some phase space distribution, and you go back here and see how it improves and adds on top of the usual picture that we have. So when I impose, yeah. So to be clear, when I put a lambda cutoff here, suppose I take lambda, suppose I trust these equations, and I take lambda and bring to infinity. So taking lambda to infinity means I trust this equation 100% down to very small scales. It means I consider, if I assume it's a perfect fluid down to very small scales, it accounts for taking lambda and going to infinity. But the whole point is that we know that at some scale, some nonlinear scale, it's going to break down. So we of course don't trust this equation down to, you know, this scale at the scale we are now. We know shell crossing happens way before than this. So we know this equation is wrong way before thinking about, you know, planetary physics or something like this, right? So we know this equation has to break down at some point. We know there's a scale, which we call K and L, in which nonlinear physics become relevant, in which this approximation here breaks down. And this happens exactly as I was saying before, that it happens exactly when the velocity lines cross each other. So when you have, in one single point, multiple velocities, and this is what we call shell crossing in structure formation. So we know the shell crossing scale happens around something like 0.3 h over megaparsec. So we know around this scale, this approximation has to break down, because then you have to include something like this term. And the fact that we are missing this term, and the fact that we are missing a dynamical equation for this term, means we don't trust those equations anymore, okay? Yeah. Yeah. So when you think about, so this is collisionless dark matter. With the fact that we have a 0 here means it's collisionless, right? If you had some collision, some interaction with other sectors, this would enter also those equations here. I mean, on different ways, depends on how you put those collisions, of course. But normally it would enter as some extra term here on this right-hand side, okay? You can think, for instance, about interactions with, I don't know, baryons, for instance, or something like this, or interactions with dark radiation or something like this. And this would enter this right-hand side as some extra gamma here or something like that, okay?
So just to be clear, what do you mean by perfect fluid approximation?
So I mean, each point, I mean that the lines don't cross each other. So when I think about velocity lines, I can associate to every single point one single velocity, okay?
Shell crossing by definition?
Yeah, by definition, exactly. Shell crossing is the opposite, in which you have basically the fluid lines crossing each other, right? Or something like this. So this means you have two different shells in which you cannot associate to one single point, one single stream, right?
So even considering anisotropic stress would still be perfect fluid.
So for anisotropic stress, I think you have to add some components here for sigma, right? So I'm dropping this term. Perfect fluid means I can drop this term.
Why? You can have perfect fluid with pressure.
So this is pressureless perfect fluid, right?
Right. But the perfect fluid can have pressure.
Yeah, it can.
And then you have this term.
Yeah, then you would have an extra term like this. So that's why I'm considering not only like a perfect fluid, but a pressureless perfect fluid. That's right. Not only this part, but the fact that you also don't have as you said, you don't have a pressure generating sound waves. Okay? Yeah?
Sorry, but a perfect fluid can have an anisotropic stress. That's fine.
A perfect fluid can have an isotropic stress. So what I mean here is that this term can be dropped. And so this is what I mean. And this
This is pressure.
this is a pressureless perfect fluid.
So can a perfect fluid with pressure can have an anisotropic stress?
Okay, now I don't think so. So for me, it means like you can drop this term. It means that it has to be both pressureless. I think if it's not pressureless, you can still have a term like this.
So
And
perfect fluid can be pressureless and have an anisotropic.
I think so. Right, and something else just to comment is that sometime I'm going to use this abuse of notation, which is defining a phi tilde, which is phi over 3/2 8 square omega m. And I'm just going to call this phi, because then this equation is going to read nice. I'm just redefining my phi. It should be something like delta square of phi equals to delta. Okay. Okay, how much time do I have before going for lunch? Yeah, so this means extra 1 hour, right? Okay. Yeah, I'm going to try to finish those notes. And I'm not sure if I'm going to make it, but right. Okay, so then the equation of motion, if I take those equations here and I define something, which is the divergence of the velocity, which means taking basically the derivative here, I can reach and take the Fourier transform, of course. I'm going to get something like so those are the equations I had before. I'm also assuming here no vorticity, because you can show that vorticity, if you consider vertical modes here, you can show that vorticity also decays. So I'm dropping the vorticity assumption. So there is, of course, an extra component here, which is not only the one you can get with the divergence, but you can also get the rotation of V. And I'm just dropping it, assuming that there is no vorticity. I also recommend this paper here, in which they explore vorticity. And in which alpha is equal to P12 cross P1, P1 square, and beta is equal to P12 square, P1 plus P2 over 2, P1 square, P2 square. Right, so as I said, this, the right-hand side here of both this equation and this equation is the nonlinear part, right? So here you have a coupling between two different modes. The coupling is given by this alpha and beta. So this coupling is basically a product of momentum. So this is the dimensionless coupling, in which you have these modes P1 and P2 coupled to form basically a mode K. So physically, the way we can understand this coupling is that we have a mode P1 and a mode P2 interacting to form some mode K, right? So this is a vertex. This is what we call vertex. An interacting vertex. So if you just take the Fourier transform of this, take the derivative of this equation, so here you have this equation to take the derivative. So this is exactly the same equation as I had before, but in Fourier space. So this, for this one, I'm using the Poisson equation. Okay, so this part is the Poisson part. And for this part, it's just basically the coupling. So here you have a nonlinear coupling between delta and V, and this becomes the right-hand side of this. So the second term, the theta part, basically is this part here. Okay? So this is basically theta, and this is the right-hand side. And for the Euler's equation, here I have exactly the same. So here I have the right-hand side, and here I have this omega m h squared delta term, okay? So this is linear, just because I can connect this part to this. When I take an extra derivative of here, I take an extra derivative of this, and I get a delta, okay? Is it clear now? Yeah? So alpha is not symmetric, but you can symmetrize the kernel later. So the symmetrization of the kernel is something that's going to happen later. But alpha here is not symmetric. Okay, just to comment something relevant here is because as you see in the equations of motion that we have basically two fields connected, which translates in terms of vertex as a triple vertex, right? And something we have in EFT of LSS is that always the vertex that we have are of this structure. We have only triple vertex in EFT of LSS. Just because the equations of motion have coupled delta and theta and theta and theta. Yeah. So, sorry, what? Yeah, those are exactly the same. So this is both alpha and beta. Okay? So we can either have here delta and theta. If you have a delta and theta, this would be an alpha. And if you have a beta and beta, theta and theta, this would be a beta, okay? So in EFT of LSS, always, since in the equations of motion, we have something like a quadratic term, it means that in the Lagrangian, we would have like a triple vertex. So this is right, like this is a very tricky question. People have tried to do it, but the answer is so far, no. Like it seems that we don't have a Lagrangian description. So there's a paper from Matarazzi, I think it's 2006, in which they tried to do it. You can, of course, come up with a Lagrangian, like something you can do is plug the solutions of the equation of motion with a current in a partition function, but you cannot find directly a Lagrangian that gives exactly this prescription. Just because, like exactly, like you have to find some, at least for the EFT part, you have to find some UV completeness for this, and this is quite tricky to get in the Lagrangian part. Right. Yeah, here we are dealing directly with the things in the equation of motion level. And the symmetries still, so when I think about the symmetries of the problem, as I'm going to mention later, it's about parameterizing how this guy that we are actually dropping can depend on the symmetries of the problem. So the question you have to address is how this guy that you're dropping can actually depend on the symmetries. Okay? But I agree, like ideally, it's quite different from what we do in particle physics. So here we're dealing everything directly in the equations of motion, the level of equations of motion. Is it clear now? Right, so let me now go back and again drop the nonlinear part, which is the right-hand side of those equations, and focus on the linear theory. So I'm going to briefly go through this because this is rather So this means, so this is what we normally see in cosmology classes. So if you drop the right-hand side of those equations, then I'm going to use, if you just drop this part of the equations, sorry, this part and this part of the equations, then I'm going to use the notation 1 here to refer to linear density fields and velocity fields. And we can get an equation for delta tau of delta 1 plus theta 1 equals to 0. Theta 1 plus h theta 1 plus h squared delta 1 equals to 0, in which, since we have two equations, we can transform them, like we have two single first order ODEs, which we can transform in a single second order ODE. For which we can get the solution which is called the growth factor. So the growing solution is delta 1 of x and tau is equal to delta 1 of tau 0 and x d of tau d of tau 0. So this is just some reference tau 0, which we take today to be this tau 0, in which d of tau 0 is equal to 1. Such that when we plug this solution, the growth factor part here, we gain a solution, we gain an equation for the growth factor, which is delta 2 of d minus h delta t of d minus 3 halves h squared d equals to 0. And this has a solution in Einstein-de-Sitter. So this only depends on time. And in Einstein-de-Sitter, in which we are dominated by matter, we know that d of tau is equal to a of tau. Okay, now we know the solution for the matter part, but also for the velocity part, theta 1. We know, using this equation now, we can now find a solution for theta 1, in which d tau of delta 1. So we can relate delta 1 and theta 1. So we can find a solution for theta 1 as a function of delta 1. And what comes here is what we call, okay, we can just change coordinates. Okay, should have d a. So this is just a co-moving Hubble, and this is what we call f. So theta 1 is just minus f h delta 1. So we can find a solution for theta 1 as a function of delta 1. So at linear level, both velocity and density are degenerate up to a factor f h. Okay? So the linear solution for them is the same. And in Einstein-de-Sitter, we know the solution. It's just the growth factor, which grows linearly with a. So I wanted to show a plot now. Right, so this is just the growth factor for two different cosmologies, EDS and lambda CDM. And what we see here is that the growth factor In red, you see for Einstein de Sitter, and in blue, you see for lambda CDM, and you see that both are quite similar to each other. So the idea here is that we use the solution that we have for Einstein de Sitter, and as you're going to see for perturbation theory, we are going to use this solution, which is exact for Einstein de Sitter, and plug this in for lambda CDM. Okay? So this is just the growth factor for the two different cosmologies. Right, so let's move now to the third part, which is now going beyond the linear part and considering nonlinear theory. Now I'm going to consider this solution as the full equation, these equations like entirely, also considering the right-hand side of those equations. And I'm going to plug in the perturbative ansatz that I had before, in which I write down delta as a sum of delta n, and also theta as a sum of theta n. Oh, here, on the right-hand side, I think you have an age here. Or depends on how you define the whole theta. If you want to keep this f here or not, depends on how you deal with this. But there is an extra factor here. I think it's an age or... Oh, sorry. Yeah, so you're thinking about the a here inside. Okay, so let me write down everything here. So, okay, I'm going to write down this as x and tau, x and tau. Then you don't have an a, okay? Then my ansatz that I wrote before, which is that delta n of k and tau is going to be equal to delta g, delta d hat minus p1 n delta 1 p1 delta 1 pn. But now I'm going to promote my kernel f p1 pn to be some generical time functional too, okay? So to address this question, Rogero, now I'm keeping the tau here as well, okay? So as you're going to see, this f now depends on tau, and this, for Einstein de Sitter, is exactly the a factor that you get here, okay? And also similarly for theta, but instead of having this f here, you have a g here. Yeah, so this is k minus p1 minus p2 minus pn. So this is just a convolution, okay? To say it's a convolution between delta 1, delta p1, and delta pn. Right, so if you plug these ansatz here onto this equation, you get something that's the following. So you get a shape for f and g. So if you just take this solution and put inside this equation here, you know, without the ones, of course, because I have the right-hand side, then it means I can find n by n for each one of the n's. So for n equals 1, I find exactly these equations here. And then I take for n equals 2. For n equals 2, I'm going to have basically n delta t of delta 1, delta 2 here, plus theta 2. is going to be basically delta 1 and theta 1, which I already know because I know the linear solution. So I can order by order basically take two fields here and take the sum of them and say, ask yourself what's going to give you the equation for theta n and delta n. So just to show you an example for Einstein the series, sorry, this is actually 2.3. Yeah, let me go to the other side. I think it's better. So if I have these ansatz here again, delta n now of k and tau is equal to a to some power n delta n of k. So here I'm separating the time dependence, which comes here, and the space dependence that comes here. I can see that actually the solution is exact. At least when I go to Einstein the series, I can find that the solution here is exact because I can just plug this solution here onto those equations, and I find that n delta n minus theta n is equal to a sum in I of an integral of P1 and P2 of theta n minus I delta of I P1 P2 alpha P1 P2. So this is the first equation. Now for a generic order n in Einstein the series. And the reason why in Einstein the series it's so simple is because at least for the second part, for this part, which is delta m, you can replace this by 1. And the Hubble part, you can replace this. You can just substitute the fact. You can use the fact that delta tau h the n is equal to n h to the n Hubble. And you can use delta t of h to the n is equal to h square h to the n and minus 1/2. So for Einstein the series, we have those two identities here. So yeah, generic, like those two identities of course hold always, but for Einstein the series, you know how this guy behaves, you know how Hubble behaves. So it means you can solve them exactly to get this equation for continuity and this equation for Euler's equation. Okay. But notice that here the time derivatives have gone because I have used this, simply this. And now I have two equations. Everything here depends on k, of course. Such that I can find a solution. I can find a solution for each one of those n's as a function of sums of i's for theta indexes here and delta index here, which are lower than the order that you have. So here, I goes from 1 to n minus 1. Okay? So this means that I can recursively generate solutions for this, for each one of these theta n's and delta n's. So then you have the delta n, for instance. You can take delta n to be 2 times the right-hand side of equation 2. Let me call right-hand side 2, plus right-hand side 1 of equation 1 over 2n plus 3 and minus 1. So if you just take the right-hand side of equation 2, which is this one, plus 2 times 2 plus n plus 1/2 right-hand side of equation 1, and divide by 2n plus 3 n minus 1, you get a solution for delta n. And this gives you an equation for Fn. Again, the fact that I'm using ICTP-SAIFR here is very important because it means I can go to those kernels here, those F kernels, and separate them as equal to F P1, Pn. There is an n here missing, sorry. A to the n. And the fact that I can have this is exactly because in ICTP-SAIFR, I can have a closed formula. I know omega m is 1, and I know how age is for ICTP-SAIFR, such that I can just find this exact solution here. Okay? So this means I can find a solution for Fn of P1, Pn. Is it clear? So now you see why ICTP-SAIFR is so simple, because the equations become exact here in this case. And for theta n, you can do the same. But now it's equal to 2n, right-hand side 2, plus 3/2, right-hand side 1, divided by the same guy here. So it's exactly the same, but so, sorry, what? Sorry, right-hand side of 2 means right-hand side of this equation here, 2, and right-hand side 1 means right-hand side of, sorry, this is equation 1, and this is equation 2. Okay? So you take the right-hand side, which is the nonlinear part of equation 2, and you take the nonlinear part of equation 1, and here it's the same, okay? So this means I have a closed formula for Fn, a generic Fn, and also for Gn. So just to show you one example, the F2, yeah, I don't need to share, it's just, yeah, I can write down. So it's 5/2 and 2/7, okay. No, yeah, I can write down, yeah. So for instance, F2 of P1, P2 is equal to, 2/7 plus 1/2 P1 over P2 plus P2 over P1 plus so this mu is just the angle between P1 and P2. Okay? So you see it's a dimensionless kernel in which you have P1 and P2, and you have basic ratios of P1 and P2, and it's just dependence here on the angle of P1 and P2. This guy here, it's the angle mu, 1, 2. So this is So here in this part, so yeah, so what you're calling here is, so this part here is actually a bit tricky. So the fact that you have this part here is something intrinsic of the Eulerian framework. So as you said, as this guy goes down to 0, this guy diverges, right? But when you have the, so this is what's called the displacement cancellation that you have. So this term cancels out when you consider alpha F2 plus F3. So this is a part that cancels out. And it's just here because we are in the Eulerian framework. And when you go to Lagrangian framework, it cancels out. Okay. Yeah, so those divergences here, they cancel out when you sum everything together. Actually, so those, sorry, there are two different kinds of divergence, sorry. So the, right, so here, let me, so there's something called IR-safe integral. So this is what Roger is asking. Like when you take P2 and bring to 0 and P1 and bring to 0, in principle, you see that there would be a divergence here. But there is something called IR cancellation, which is the fact that you, when you sum F2 and F3 together, which is what appear at one loop level, those divergences here cancel out. So you have to consider, when you do like numerically, you have to be very careful like when you compute those things numerically, because if you sum, so this guy is gonna source this P22 diagram, but you always have to compute P22 plus P13, because there are some divergences here that cancel out exactly the divergence that appear here. Okay? Yeah, thanks. Sorry, can you repeat? Yeah. Yeah. Yeah, you have everything safe when you sum them, because those divergences are not physical, such that when you take the displacement, so those comes from the displacements that basically cancel out. So there are some displacements that appear just because you're using something called Eulerian picture. I don't want to dig inside this because it's a bit complicated. I'm going to mention in some slides later today, but when you sum those terms, basically those divergences cancel out because the displacements that source them are basically canceling out each other. Okay? It's a bit tricky, but it's called IR-safe. And you can show that when you sum both things together, they are IR-safe, actually. Yeah, good question. For the tree-level bispectrum, but for the tree-level bispectrum, you also don't have any integral, right? For the tree-level bispectrum, so yeah, okay, just to, it doesn't matter, but just because, okay, the tree-level bispectrum is this. So Carol's question is related to this, right? So here you have K, let's say P1, P2, and P3, right? As the bispectrum, you have three different components, right? So Rogero's question is like, okay, you have this divergence because you can always bring P2 to be 0, right? Because you're integrating, like inside those guys, you're integrating over the piece. But here you're not integrating over anything. It's tree level. Okay? Yeah, because here those guys are integrals over P of those F kernels. So this means I'm integrating from 0 to infinity. Here I'm not integrating anything. There are no loops here. Yeah, everything I write down here is in a Eulerian frame. I'm going to explain the difference between Eulerian and Lagrangian later today. I mean, I have one slide for this, but if when I go to Lagrangian, those things don't show up, those divergences. Okay? Right, so just to finish this part, I'm gonna, yeah. I think I can go to the next, yeah, I'm gonna finish the correlators and extend the loops. Just to say that if you go beyond EDS, the only thing you have to change is instead of considering. So as I said, this f here for EDS factors out as the space part and the time part factors out here. So we can write down this equation in which we have space and time separate, right? So the question is how to generalize to beyond EDS. And as I was showing before, if you take the growth factor D, so what's A here? I can write this as D EDS to some power n, sum of delta n, right? Because as I was saying, for Einstein-de-Sitter, this solution is exact, and D is equals to A, okay? So if you go beyond Einstein-de-Sitter, the only thing you have to do is to generalize this. So this is a question, actually. What happens when you go beyond Einstein-de-Sitter? Can we just use D to the n delta n? So this is an assumption we take. So this is an approximation. That's valid up to some limit, of course, but you can show that this is a % approximation, and this works pretty well. So we just generalize this, writing down as a growth factor to some power n times delta n, okay? Just because, oh yeah, sure, at least, yeah, of course. Yeah. Okay. And the reason for this is because if you go beyond EDS, you cannot solve the equations anymore in which like time and space separate each other. You have to consider some approximation for the time derivatives here. So the time derivatives here cannot be written as some n times delta n. You have to consider the full time derivative again. And this leads to something called like the scale-dependent solution, which are a bit more complicated, but then you can just assume that this is true, that you can factor out space and time, and you can show that it corresponds exactly like, to a good extent, this approximation is very valid, and you can live with this. Okay? So in Einstein-de-Sitter, this solution is exact. I know this is linear. Yeah, exactly. Exactly. And you can show that what appears here, so basically the growth factor is just telling you how the linear solution grows. So whenever you have this, you have basically n entries of delta linear, which means you expect this to grow with the growth factor to the power of n. That's why you have this ansatz here, right? It's not something like going from here to here. It's just saying that you expect exactly the growth modes to grow with the growth factor. And you expect them to factor out in Einstein-de-Sitter. Of course, it doesn't happen for other cosmologists, but to a good extent, it happens, and it's a good approximation. This was shown. I can recommend some papers. So you can see, for instance, Garni plus the Paulo 2021, I think. I'm calling, well, if for matter domination, unless you have some subcomponent, like if it's matter domination, you have some corrections on top of this. If you have some extra components, you have some extra piece here too, right? This is Einstein-de-Sitter only. I mean, I'm calling omega m equals 1 Einstein-de-Sitter. So if you have some subleading component, of course, like it's A plus some corrections. But everything boils down to the fact that for Einstein-de-Sitter, this part here becomes easy to solve. And also this time here, this part here also factors out, okay? I'm going to get you this. In terms of diagrams, it's very nice and easy to explain. I'm going to explain in terms of diagrams how it goes, okay? But the idea is actually very, very beautiful. I mean, I can show you later. Right, let me just, to finish this part, let me just go from the fields. So far, we have only dealt with fields. So let's deal with correlators now. So as I said, for cosmology, what we want in the end is something like delta K1, delta Kn. Okay, so this is what we ultimately want to calculate. So we want to calculate correlators. So then the whole idea boils down to take this solution here that we had and plug inside those correlators. So everything here is just, can be written down as a sum, different sums, and 1 of delta and 1 So you can just take these to be products of correlators of different delta n fields, such that, for instance, for the power spectrum, for the 2-point function, you have delta K1, delta K2 being equal to, sorry, in which each one of those guys is written as, so this is delta 1, delta 1. This is delta 2, delta 1, and so on and so forth. So here I'm just saying that the remainder part of this equation is just delta 1 to some power of 5. I'm just truncating because here I have 2 delta 1s, delta 1, delta 1, so it sums to 2. So here I have 3, here I have 4, here I have 4, and here I have something that's 5, order 5, okay? So this is an expansion in delta 1, again. And this part here, which is 1, 3, I'm going to write down this. Okay, so this one here is very clear. And this is the tree-level contribution. What we call. And I call it tree-level because it doesn't have any loops. It's just the linear power spectrum, which is the usual one that we know. So this is, you know. For the 1-2 part, I'm going to show it 0. And the reason why it's 0 is because P21. Okay, I'm going to calculate 2 of them to explain how to calculate them. I think it's instructive to go through the calculation. So write down the expression for those. So K1, K2. So this is delta 2, which means it's an integral of delta of Dirac, K1 minus P1 minus P2. Let me call P1, 2. Delta 1 of P1, delta 1 of P2. Okay? This is this guy. And this delta 1 of K2. I can take this correlator, so this is P1, P2, of course. This expectation value I can bring inside and use the fact that delta 1 delta 1 delta 1 is equal to 0 because we have Gaussian initial conditions. Okay? And then we can calculate F2 contracted with F2. So P22 is equal to an integral K1 minus P1, 2. Oh, sorry, there is an F2 here missing, right? There is an F2 of P1, P2. Of F2, P1, P2. Another integral, so here is in P1, P2. Another integral in P3, P4. Of F2. Okay. And then there are three different ways to take this contraction. So this contraction I can write down as subproducts of those other contractions. So the first contraction I can take is P1 and P2. So if I take this contraction here, I find something like, I'm going to find a direct delta of P1, 2. So it means P2 is equal minus P1, which means this F here is going to be F2 of P1 minus P1, which is 0. If you just plug here, you're going to check it's 0. Okay? So this first contraction is actually 0. So it means I can forget about this first contraction. And the other two contractions, which is P1 with P3 or P1 with P4, are symmetric. So I can write it down as 2 times P1, P2. K2 here. K2 minus P1, P3, P4. F2 of P3, P4. And then this contraction I can write down as the subproduct of the two other contractions. So I'm going to contract this with this and this with this. Okay? So this is equal to delta 1, P1, delta 1, P3, delta 1, P2, sorry. There's a 2 missing here, which is this 2 here. P2, delta 1, P4, which is equal to 2, P1, 2, P3, 4, P11 of P1, P11 of P3. Okay? So then P12 is basically, sorry, this is P13, and this is P24. So P13 means I can write down this guy. I can remove the P3. Let me remove the P3 and P4 integrals using these direct here. So it means this guy here becomes the same. And sorry, there is no integral here anymore. And then you have something like P3 becomes minus P1, P4 becomes minus P2. So this is a Dirac of K2 plus P12. F2, P2, P1 minus P1 minus P2 times P11 P1 P11 P3 is minus, sorry, so here is P2, right? Here is P2. P2. Then I can just, oh, it's better like this, no? Hello, hello, yeah. Then I can just see, is it better like this? Same? Okay. Then I just get, okay, so F2 of minus P1, P2 minus P2, I can just, this minus sign, I can always show, like, it's something I can show that for the F kernels, you can always take the overall minus out, which is they're equal basically to this. So this is basically equal to this. Because you can always take the minus of all arguments and remove it, like this is something you can always do. So I'm gonna remove this guy here and write this as a square. Then I end up with an integral over P1 and P2. And I can use one of the Diracs here to integrate it out, such that I end up, so yeah, so I integrate over P2, for instance, such that I get something like 2, K1, 2. Okay? So when I integrate over P2, this is just going to become K1, 2 here, and I get an integral. I can call P, instead of calling P1, I'm just going to call P. And here I'm going to have F2 of P, K minus P, P11 of P, P11 of K minus P. F2 square, yeah. So diagrammatically, there is a picture like, okay, we can think about this as being, yeah, I'm gonna talk about the diagrams later, but yeah, I'm gonna start the next lecture talking about the diagrams. But just to finish, you can do the same for P13, and you're gonna see it's equal to 3 times P of K, K1 if you want, integral of F3, P minus P, K of P of P, P11 of P. Here is K1, 2. Here? This? Oh, sorry, K1. Or K2, doesn't matter, right? No. Yeah, because there's another K here. Yeah, it's K1, but it doesn't matter because it comes with a Dirac here in front, too. K1, 2. Because by translation invariance, you always have this delta of Dirac here of Q. Okay? I just noticed I've been a bit sloppy because I get a delta of Dirac of K1, 2 and a delta of Dirac of K1, 2 here. So I should call, I don't know, so yeah, let me remove this from the definition, okay? So the definition of this guy doesn't have the delta of Dirac. Okay. Yeah, it appears there. Okay. Right, so in the next lecture, I'm going to talk about the diagrams, how to construct diagrams, how to correct it with the EFT of LSS. And yeah, I still have, 10 pages, so see you this afternoon.